Hello, everybody. This is the high-level panel on advancing water management and through research. I want to thank all the panelists for joining us, as well as everybody that's online. I hope people are enjoying the online meeting. I think a lot of effort has been put into pulling this all together, and it's much appreciated for sure. So, like I said, I'm happy to sort of help moderate the discussion. I hope I don't do too much talking. I think we have a nice panel here of people, a nice diverse or a range of expertise. So I'm excited about the discussion, and hope you guys are too. I think we'll start with just a round of introductions. I'll just call you out. I think I'll go alphabetical by first name, and then we'll get into some of the questions that are being posed to you folks. So I'll send it to Dawn first for a short introduction, please.
Scano, hi. I'm coming to you from Six Nations, the Grand River. I'm Mohawk, cultural anthropologist, PI of a few GWF projects and COI on others, and really happy to be here and happy with the work that GWF is doing. Thank you.
Awesome. Thanks, Dawn. I hope my alphabet's right. Julie?
Yes. Hi, everyone. My name is Julie Theriault, and I'm a Canada Research Chair in Extreme Winter Events. I'm also a full professor at the Department of Earth and Atmospheric Science at the Université du Québec à Montréal. My research expertise is on the theory, simulation, and observations of precipitation during the cold season, and also I focus on various time scales. So one thing I focus, one of the big challenge I think in the field is predicting and being able to measure the precipitation, including the timing, the location, as well as the phase and the amounts of precipitation.
Nice. Merci, Julie. Laurie.
Thanks, Chris. My name's Laurie Bradford, and my pronouns are she, her, hers, and I identify as autistic. And I encourage everybody here to introduce yourself with those micro inclusions to help with our inclusivity at the conference. I'm coming to you from Treaty 6 territory in the homeland of the Métis. I am a social psychologist. I sit in the College of Engineering in the School of Environment and Sustainability at the University of Saskatchewan. And my research is around incorporating social and cultural sciences into more technical fields like engineering design and hydrology and modeling in other different ways. I'm happy to be here also as editor of the Engaged Scholar Journal, and I look forward to sharing on this panel.
Thanks, Laurie. I am a he, and Martyn.
Yeah, hi, Martyn Clark. I'm coming to you from Treaty 7 territory near the Bow River. I'm a professor of hydrology at the University of Saskatchewan, based in Canmore. And in Global Water Futures, I co-lead the core modelling team with Al Petronero. And in terms of my research group, I lead a group in computational hydrology. Pleased to be here. Thanks, everyone.
Cool. Thanks, Martyn. Philippe.
Good afternoon. So I'm Philippe. I'm Philippe van Cappellen. I'm a professor and a Canada Excellence Research Chair laureate here at the University of Waterloo. And I speak to you from the land that was promised to the Six Nations of the Grand River by the Haldimand Accord. So my research focuses on water quality and how water quality relates to aquatic ecosystem health and the provision of ecosystem services. I also recognize that one of the key challenges in my line of work is the highly multi-dimensional and multifaceted nature of water quality. In fact, there is no generally accepted definition of water quality, even among researchers in the same scientific field. So I'm coming here from the perspective that to meaningfully inform water quality management, we need science and models that deliver data, information, and knowledge that is not only at the appropriate physical and temporal scales, but also appropriate for a given socio-ecological context and can be translated into actionable policy and management.
Thanks, Philippe. Well said. Just a second. Some now noisy is going by. Hi, sorry about that. Yeah, so I think the first question that's been posed to us is really comes from a place where that recognizes that the volume and quality of research that Global Water Futures has created is much of it is, we hope that it helps inform water management decision making. So I guess to start, I'd just like to ask if any of you can provide some nice examples of places where your research or somebody else's research has contributed to water management, or a particular decision that has been made by policymakers or water managers. Dawn, can you go first, please?
I couldn't hear. I don't know.
We seem to have lost Dawn for a moment. So maybe while we try to get her back, can I pose the same question to you, Julie?
Yeah, sure, I can start if you want.
Thanks.
Oh, I think Dawn's back.
Oh, Dawn's back?
She's back, yeah.
Okay, no, go ahead, Dawn. If you can think of some nice examples of research that are related to water management, that'd be great.
Okay, so everything was working perfectly until it started, and of course my Wi-Fi is going down, so I didn't hear anything. And I think other people should go because I keep losing your all photos, so it might cut off in the middle of it. So I'm going to move to try and get a better reception. I'm sorry.
No, totally get it. We've all been there, I think, the last couple of years. Julie?
Yes, sure, I can start. I can start by giving my a perspective from atmospheric science on the major accomplishment on water management. I'm part of the core modeling. I'm also part of Pillar 3 and Pillar 1 projects, and mainly contributing to the atmospheric science part. And I think the advancement in research in water related to water management is especially related to the production of precipitation or no precipitation, such as drought occurrence. And for example, what we need to know is, as precise as possible, how much water, if any, and in which phase it will be produced in the atmosphere and when it will reach the surface. And these can be addressed on various time scales. For example, if we think about the management of electric dams for power generation, in which we worked with electrical utilities in Pillar 3 projects. So the amount of water that accumulates during the cold season or during heavy precipitation, it's important in the case of the phase and the amount of precipitation that accumulates. And also the chain of events during that season. And these are factors, like I said, that's been studied in GWF. If we look at another example, for example, that was addressed in other projects, for example, in Yangping Li's group about the water research on the growth season, at where the precipitation will be formed, the timing, including the type of precipitation in the summer, like the occurrence of hail. And so if I give some examples related to the modeling, for example, for the modeling in GWF, we use atmospheric and climate models that were at the resolution where the convection is explicitly represented, where the resolution reach 4 kilometers or less. And this has many advantages to do such calculations, for example, like I was saying, the exact location, the amount and the phase of the precipitation. And these grade spacing also, it's also much closer than what the hydrologists are using for their modeling activities. So these climate modeling activities were done in close collaboration with NCAR and also Yang Ping's research group. So in terms of atmospheric science advancement in research, there was a major investment into understanding the atmospheric processes. For example, during the warm season, where the convective activities over the prairies were studied, and their changes in the future, as well as changes in the occurrence of hail, for example. And during the cold season, we studied changes in the freezing precipitation and how these are related to the local features, for example, the topography. So an example, some research was done over the province of New Brunswick, where we found that the Mount Carleton, which is only 800 meters high, has caused some cold air damming and then can cause long period of freezing rain. In terms of processes that what we learn, we use the field experiment and observations. So that was a Pillar 1 project, the storms and precipitation across the Continental Divide, where the moisture and the condensate flux were studied across the Continental Divide in the southern Canadian Rockies. And then what's interesting about this is that we looked at the processes of, we have what is happening in the atmosphere where there's no physical boundary like at the ground, and then we look at in which condition it crosses the divide. And this has a big impact on the water management at the surface, because the moisture that comes from the prairies of the Gulf of Mexico can either cross it and then flow in the Pacific Ocean or not. So these were our examples of accomplishments that were done in GWF, and they also led to further questions and path to move forward on these topics.
Great, thanks, Julie. Dawn, are you? Sounds like you might be good to go.
I think I might be good to go. Let me know if it breaks up. So Aniganos is actually 3 projects that the community was frustrated with because they're different pillars and names. They just said, can you just call it Aniganos and we'll know it's water, global water futures research. So they kind of repackaged it, and they see it as one entity. So it has about 8 sub-teams. But what we're here to talk about today is specifically around water management and governance components that we're doing. What we found out in our research here at Six Nations is the Grand River it has not had sensors along the reserve boundaries. So you have sensor data before Six Nations and after Six Nations, and I did ask them why, and they didn't really have an answer. So we're pretty sure that we need to catch up, if you will, with all the other data. And we know that the waters here are quite polluted. There's been studies on the creeks by Patricia Chow-Fraser, and Tariq Dean and Atlif did a climate change study. And we are going to be dealing with, heat waves and algae and as well as flooding. And these are things that the community is wholly unprepared for. So they really appreciate what they consider to be actionable, solution-based research. They were afraid that we're going to come in there and just get research and then close down, which I'm still afraid of, to be quite honest, because we're just now getting a grounding, if you will, of data that has not ever been collected before. And I don't know if people are aware, but Indigenous data, it was generally owned by the government. So we can't even get original data. Six Nations will have a difficult time. Let's say we wanted to look up certain health data to do longitudinal understandings of how what we call waterborne diseases might have been impacting Six Nations. And so therefore data sovereignty management is really important to First Nations all across actually the globe. Because of colonialism, the kinds of data they collected were not what we would consider useful or informed in terms of the questions that the community has, the leadership. So some of the things that they're most concerned with, I have not been able to tackle yet. And one of those is the aquifers, the groundwater. They're really worried about the amount of water extraction happening by Nestle and now Blue Triton, 3.6 million liters a day, while 90% of the community goes without access to clean water. While they do have a duty to consult, and that is the new Trudeau federal arrangement, needless to say, we were not consulted and have not been consulted, but the youth that work with Oneigenos did deliver a cease and desist order to them. So they're working on a number of fronts in terms of governance, including developing a policy of water law informed by Haudenosaunee ethics, or what we call the Great Law, which is our constitution, if you will. It's more than a constitution, but, you know, they've looked into personhood rights for the Grand River. One of the things the clan mothers would like to see happen, and again, I'm just now being able to do this discussion, is looking at, you know, they believe that if the water could just flow freely, it can clean itself. It's a very basic understanding of the natural world. And there's 42 dams on the Grand River. We have 25 waste treatment plants upstream, and we haven't waste that has PCBs, carcinogens, things that were put in Roundup, if you know what Roundup is. So we know the pollution is uncleanable. And yet that is the source water for the water treatment plant that Six Nations built. So we are in flux, and we're just getting a handle on things. Much gratitude to GWF collecting data. But on the other hand, we do always end up in this position where now that we're moving forward with being able to get a handle on our waters, trying to be included in governance of our waters, which we're not in Canada. There's no policy under the water policy of Canada. First Nations are not included. So there's a lot of work to be done, and we're just beginning to find out how much. So thank you, Nawi.
Thanks, Don. I think that was also sort of actionable and informed research. That's a really good point among many. Laurie, do you want to go?
Sure. Can you hear me?
Yep.
Okay, thanks. Thanks, Chris, and thanks, Don, and thanks, Julie. When I think about the big question that you've asked us about Global Water Futures Program, I think about two things. And the first is participation, and the second is cooperation. And I think that makes for real impact of the research that has been completed by Global Water Futures so far. So I'm going to ask Josh to share my screen with everyone. I wanted to show two figures from some work by Laura Basco-Carrera and her team. And it's all about participation and collaboration in integrated water resource management. So if you look on the right side of the screen, there's this ladder of participation for water resource planning and management. And I'm going to invite everybody that's here today to think for a minute on how you are participating with the ultimate knowledge users that you want to take up lessons from your work. You know, do any knowledge users out there know about your work and what's happening? Do they have a say? What kind of information is being transmitted? Is it just one-way transmission of information, or is there back and forth? Are there consultations where there's already choices set forth for people to choose, or is there discussion? And then have you actually moved into the level of co-design and co-decision making? So I thank Dawn so much for sharing what she has with her programs. And I would say that her programs are in that co-design and co-decision making area where knowledge users, I don't like the term stakeholders, have a sense of ownership and are committed to the work, and they have a mandate to act on what they find. So once you figure out where your project is on that ladder, move to the figure on the left side of the screen and figure out what your participation and cooperation is. So along the cooperative continuum, are you just providing information? Are you coordinating activities together? Are you collaborating in a mutually beneficial way? And are you committing to joint action? So these are questions you should have in mind as you're going about your work, especially as we get to the end stages where deliverables are being produced. So Josh, you can stop sharing that now. I just want to talk about one particular project that I've been involved with, and that's a proof of concept project on agent-based modeling for flood prediction and health effects on reserves. And partners in this work have been Yellow Quill First Nation in Treaty 4 and James Smith Cree Nation in Treaty 6. So with those projects, we really aim toward the joint action square at the top of the continuum. I think we ended up landing in the co-design because of certain barriers, institutional ones, as well as governance barriers, where researchers could not really be involved in the joint action. But in that program, we created agent-based models that took information from LIDAR and DEM and other models to predict floods in the communities, 5-year floods, 10-year, 20-year, 50, and 100-year floods, and also to track the movements and the daily needs of community members as they describe them to us. So we built these agent-based models and we collided flood information with the daily activities of people on reserves, getting to medical appointments, the bus going to school, getting to workplaces on and off reserve, different health and other activities, powwows, the possibility of transmissible diseases, those sorts of things happening. And so for each community, we were able to come up with briefs, which included data outputs like health effects and when their health centers would be overwhelmed or supports they would need, when culverts would collapse, as well as how it would influence cultural activities. And we turned that into videos that they could attach to their operations and management budget requests every year that they submit to the government. So that kind of support was able to help these communities secure more funding in operations and management so they could help their communities be more prepared for climate events of the future like flooding. And so we didn't quite land at joint action because researchers couldn't stand by their side and say, they need this extra funding to prepare. But I think we aimed in the right direction and we made some progress on that. Thank you so much.
Thanks, Laurie. I like that. I like those figures for sure. Martyn.
Yeah, a lot of our work is at much larger spatial scales. So what we do as part of the core modeling program and as part of my broader research in computational hydrology is to develop models and methods to support water resources planning and management. So there's three main uses for the tools that we develop. One, streamflow prediction, to provide forecasts of streamflow on different time scales, and we can circle back on that as we're getting to the second part of the question later in the program. The second, water security, to understand the impacts of climate change on our water resources. And the third is to use advanced hydrology models and the global scale Earth system models so that we've got a better understanding of the role of the terrestrial hydrology cycle in the Earth system models and get a better estimate of the future evolution of our planet. So the landscape in Canada, the modelling landscape in Canada is a little bit haphazard in the sense that a lot of the forecasting responsibilities are devolved to the provinces and territories. And there's many, many different types of models that are used by different applications groups across Canada, many models that are being developed and used by different university groups, etc. And associated with that, there's been a lot of technical debt. By technical debt, I mean that people have been developing and using these models for a long time. And there's a lot of effort that needs to go into maintaining the models and doing some work to ensure that they can be applied efficiently and effectively. So what we see in a lot of the work that we've been doing is, and this is true globally, is that often people can spend 80% of the time wrangling data and configuring their models and leaving only 20% of their time for science to address some of the science questions. So what we've been trying to do is turn that around and develop approaches to increase the efficiency and effectiveness of the way that people do their hydrological modelling work. The key part of what we've been doing has been to work on model agnostic workflows to recognise that all of these different modeling groups are addressing very, very similar problems. They've all got different models, and those models have got their own end users, but there's a lot that we can do to share code and concepts across different model development groups, to develop more of a community of practice, to enable people to move forward more effectively and efficiently. So Al Petronaro talked a lot about that in his presentation this morning. The one thing that we've been doing that's challenging, there's been a huge challenge for us where it interfaces with water management, is to include water management as an integral component of Earth system models. And the challenge there is associated with the spatial scaling, because when we're trying to implement water management on large domains, could be an entire country, an entire continent, or the globe, we don't have the data that we have at local scales to support those models, and that we're seeing that there's a growing gap between the way that the Earth system modeling community is representing water management and models and the way that the integrated water resources modeling community is representing water management and the models. And there's a lot that the two communities can do to learn from each other and advance things in more productive ways. So some of the work that we're doing in core modeling now is to build a bridge between those two communities so that we can move forward more effectively.
Great. Thanks, Martyn. That was really good. Philippe?
Thank you. So I'm speaking from the viewpoint of water quality management and governance. I think GWF in general has been instrumental in helping overcome some of the traditional fragmentation in Canadian water quality research, and also in facilitating the alignment of academic research with concrete end user needs. And the example I'm most familiar with is all the efforts within GWF to address the continuing and emerging water quality issues related to eutrophication of Canada's lakes and reservoirs. Now, historically, Canadian researchers have been at the forefront of providing the scientific basis to manage excessive algal growth in freshwater environments. And this led to the implementation in the 1970s and 1980s of effective policies to reduce the emissions of the limiting nutrient phosphorus into rivers and streams, effectively saving the downstream lakes. And the poster child of this science-based water policy is, of course, the successful mitigation of algal blooms in Lake Erie. But what we've seen since the 1990s is this resurgence of toxic and nuisance algal blooms in Lake Erie and in other lakes also in Canada, despite the fact that the external phosphorus loads have not been increasing over the past decades. And it's therefore increasingly clear that the earlier command and control approach to reduce watershed phosphorus loadings to the lake may no longer be sufficient in controlling lake eutrophication. And similar intensification of eutrophication, not directly related to external nutrient enrichment, are also a growing issue for other lakes in Canada and in the world, actually. So within GWF, we have been able to develop a suite of modeling and data analysis tools that now allow us to fully couple the nutrient sources and transport pathways in land-based watersheds to nutrient cycling and ecosystem functions in the lakes. And together, these tools have provided new insights in the combined roles of on-land and in-lake drivers of eutrophication. And these drivers include, for instance, the time-delayed release of historical nutrient legacies in agricultural landscapes, the changing timing and speciation of phosphorus releases via urban stormwater management systems, and the climate-driven acceleration of in-lake phosphorus recycling. And a concrete outcome of this work, for instance, is the uptake of the results and recommendations of Global Water Futures-led research in the development of the next binational Great Lakes Decadal Science Plan. Now, to a large extent, the management relevance of the model developments on watershed-lake coupling is due to the fact that they have been co-developed in collaboration with partners such as the International Joint Commission, Environment and Climate Change Canada, conservation authorities, municipalities, NGOs, and industry associations. And I can't stress enough the importance of GWF's relatively long funding period of 7 years as a major asset in building long-term relationships of trust and respect with our partners. And this, of course, in turn facilitates the transfer of scientific knowledge to these partners. And for example, our work, or work of my group on stormwater management systems, is actually being taken up in the climate adaptation plans and investment decisions for green infrastructure by several municipalities in the Greater Toronto Area. But a final point I really want to emphasize is also the impact GWF has on enhancing public access to water quality data. And this has been touched a little bit upon by Don. And GWF has accomplished this through its own data catalog, so the GWF.net, but also via other open data repositories, in particular DataStream and the Federated Research Data Repository. And I strongly believe that open access to water quality data is an essential first step to generate a deeper public engagement in decision-making around water resources and the protection of aquatic ecosystems. And so ongoing collaborations, for instance, with the Lake Winnipeg Foundation and the Six Nations of the Grand River are clearly demonstrating the enormous potential of citizen science initiatives and community capacity building to address water quality issues.
Nice, well said, Philippe. Yeah. So we only have about 15 more minutes, but to squeeze in this second question, which is really about what have we done right, but also maybe what have we done wrong, in the sense that what could we do better and learn and apply in the future. I might just open it up to whoever would like to handle that one first. I can see there's actually a lot of overlap between a lot of what everybody has said, all five of you. Things like Dawn and the actionable informed research, and what you were saying, Philippe, about open data and citizen science. And it's clear that there's a diversity of, what's the term you used, Laurie? Knowledge users out there. And so, how do we, can we be everything to everybody, or do we sort of pick our battles and choose things? And so these are the kinds of things that I was hoping we could kind of discuss as we move forward. So if anybody wants to chime in, that's really good. If not, I'm going to pick one of you. So Dawn, I think you're maybe trying to speak. But you're still muted.
My computer wants to play with me today. I think, Global Water Futures has been a watershed for Indigenous water research, for sure, giving us opportunities we were often locked out of, definitely a lot of scientific circles, and had no pathway in. So it provided that to us. I think the ideas that the community came up with, it was all designed by community leaders who hold a great wealth of knowledge. One of the things that I think they did right was, combining the data. And for Six Nations, they wanted to develop a visual of the water quality, water monitoring. So we started developing a virtual space with virtual reality, digital stories, but also importantly, mapping real-time data so people could see and begin to understand and play with the site and begin to really become citizen scientists, and also download the sensors that Ravi and Charles are making on an iPhone app. So making everything meaningful and useful to make good decisions as community members. But I think where it could have been helpful is in the capacity development piece. So oftentimes I felt like when I'm getting, we got youth trained, or they're doing workshops, they're working on the project, they did GIS mapping, they did water testing, and I'm trying to get them credits, and I finally got that passed so that they'll get 90 hours altogether to get one university degree by the time they get out of high school. But it's exposing them to a world that they thought wasn't welcoming. I guess there's a lot of messaging that needs to happen. And there needs to be help with that on a national level. And it's not necessarily GWF's fault. It is we're doing what the government should be doing in terms of developing Indigenous capacity to, we're creating a water treatment plant operators program. I feel like I shouldn't be doing that, but I'm doing it because it's what the community needs. It's what First Nations need across Canada, because they're building water treatment plants without the training. And so virtual and simulation would be the answer. There just could have been more high-level decisions and brokering with the government that that those of us living in, don't have any titles or what have you, we just simply can't. But I think GWF, the leverage that they could provide to advocate, and I don't think it should just be First Nations. I think the ideas that Six Nations came up with are applicable to communities across the country. Everybody should be water literate. Everybody should be able to understand if they don't start taking care of their water, they're going to deal with algae blooms. They're going to deal with no access to water. So the more we can educate people, and I feel like that's the piece that could be elevated in the future. But I also understand it's not necessarily GWF's role, but they just happen to be in the right place to kind of make something like that happen. Also with the CWA, with the Canadian Water Agency, we wouldn't even know that was happening. And normally we wouldn't be talked to. So people go to political lobbyist organizations, and they don't go to the Indigenous scientists who've been working on these issues for a very long time, because we're not consultants. So we're not in their orbit. And I think that could be that was another bridge that GWF helped to somewhat build. But again, I understand, the scope of need is so great. You can't be all things to all people. But I think Indigenous needs are a little bit greater and more in crisis than the rest of Canada, although we are the canary in the coal mine, and what's happening to us will happen to Canadians. And I think the sooner they understand that, the better. So thank you.
Nice, well said. Sorry, Laurie, you
sure,
get your hand
thanks. Yeah, just thank you again, Don. It sparks some thoughts in me about globally and politically. We're seeing a movement away from the business as usual, the winning friends and influencing people and the getting to yes kind of norms in society to more adversarial. And I don't mean that in terms of an antagonistic leadership, but adversarial in that they're making evidence aware. So I think of people like Edward Snowden and Julian Assange and Greta Thunberg, who are actually using the data to call out leadership to make better decisions for the future. I think that's one way that Global Water Futures projects are providing the evidence and the data needed to ask for accountability or to invoke change. So, I give huge kudos to Global Water Futures for having the data open and available so that these political forces could be overcome and we can see change.
Thanks. Philippe?
Yeah, I think to add to that, I think indeed as a program, GWF has clearly recognized the need to address, from my perspective, water quality issues from the convergence of interdisciplinary expertise, the recognition of different knowledge systems, and transdisciplinary co-creation and so forth. But I do think that there's still much more work to be done in order to develop the necessary research practices and social processes that can accelerate knowledge mobilization at this science management interface. And again, I think there's much opportunity to move forward, even within GWF, in how we assess and manage water quality risks under uncertain future conditions, in particular, uncertain future climate conditions. And so I would even argue that there's a lot of water quality science and modeling work underway in GWF that should be even further oriented towards assessing how climate change may amplify and possibly in some cases even attenuate water quality deterioration caused by pressures such as industrial contaminants, intensive agriculture, invasive species, mining, and even urban growth. So in other words, this should enable the mapping out of how and where water quality is most likely to be adversely impacted under future climate conditions. But to translate climate vulnerability into an actual risk to the well-being of people or the health of ecosystems, we also need to evaluate the available capacity to mitigate the impacts of these changes in water quality. For instance, through the implementation of nature-based solutions, upgrades to water treatment facilities, or even and particularly adjusting the existing water governance arrangements. And so assessing and mapping the adaptive capacity to deal with change in water quality is very much where social sciences, community engagement, knowledge exchange process, etc. come into play. So I think we can imagine a framework consisting of layers of spatially explicit data, knowledge, indicators, supplied by different disciplines, different sectors, and different social actors, that when we overlay these layers, really provide a better means to perform holistic water quality risk assessments. And those assessments would then help prioritize where investments in human capital, infrastructure, ecosystem restoration, water quality monitoring, etc., is most urgently needed to ensure continued access to safe water. So these kind of conceptual frameworks that integrate vulnerability, hazards, adaptive capacities, they have been around for several decades, but their actual real-life application in water quality risk management remains very, very limited. And so I think there is scope and potential within GWF, and of course beyond the GWF, to really build on our collective expertise and momentum to demonstrate real impact in this area.
Yeah, I agree with you for sure, Philippe. And that, you know, it's taken 4 or 5 years for GWF to get here, and we've got another 2 years left. And just in my role in Prairie Water, I'm starting to freak out a bit about, you know, what can we do in the last 2 years, and what happens after that, right?
But that's
because
yeah.
And there's so much, you know, I just feel like we're starting to get on the cusp of something really good, right? And I wouldn't mind bringing Julie or Martyn into this, right? Because they're the ones helping to build at least some of the hydrology foundation or the hydrometeorology foundation of some of this stuff, and especially you know, some of those big picture continental scale or the big picture tools, right? So I don't know, Julie, Martyn, do you have something?
Would you like to go, Julie, or I can?
You can start, Martyn. Yeah, go ahead.
Okay. Yeah, so GWF has been incredibly successful in terms of what it's done in developing the modelling capabilities. It's been a massive collaboration across Canada. What I see moving forward, and this is already there in many parts of GWF, is a massive collaboration internationally. And we're already beginning to see that in collaboration with our US colleagues, and where we're able to take the tools that are being developed in different parts of the world and take the best parts of those tools and apply them to some of the critical water problems in Canada. And don't want to say much more than that because we don't have much time, but I see that as a tremendous opportunity for us moving forward over the next 5 years and more.
I think you might get the last word, Julie.
So I think, like, through GWF, we have the opportunity to use very high resolution models, and we extract a lot of good information from it. And I think a good way to move forward would be to increase our capability to develop those high resolution models, to give us a little bit more flexibility on the type of runs, the duration, and also ensemble predictions of future climate, so we can understand more on the local scale what's going to happen in the future over Canada. And also, like Martyn said, developing collaborations with more collaborations with the Americans and across the globe.
All right, I think we have to finish there, but I want to thank everybody. I thought the discussion was really great, and everybody brought up some fantastic points. So I guess we'll see what the next few years bring on this front. So thanks everybody again. Yeah, cross your fingers for sure. Thanks everybody. Bye.
Thank you.
Hi, Claude and Helen. Sorry,
Hey, how are you?
I'm good. How are you? I'm at the Giant Aquatic Societies meeting, so I'm hiding away in a room.
I'm abroad, so and it's at night right now.
Okay.
It looks like we're live.
Yes, I think we are. I think we're waiting for Ravi. And then, oh, Ravi's not here. Okay. So I'd go with, like I had mentioned, Claude and Helen. I'd go with Claude, you, Ravi, and Helen, and then me. Just spend 5 or 7 minutes talking. And Yongi is not there anymore, which gives us a little bit more time to talk. And then we can kind of see if there are questions. Will the questions, do any of you know if there's questions that will come online, or should we just start without Ravi?
Well, it looks from Josh like we're live, so I think we should start without Ravi.
Are we
live? Apparently,
are we alive? Okay.
Yes. Okay.
So I go with my the 3 questions. Is that correct?
That's what I was thinking. So let me just start by introducing ourselves. Good afternoon, everyone. Welcome to the panel on using new sensors and data sets to improve water management. And we have here Professor Claude Duguay from University of Waterloo and Professor Baulch from University of Saskatoon. And I won't introduce any of their work anymore. I just maybe ask Professor Duguay to start us off with answering a couple questions to start, but maybe talking a little bit about your work related to sensors with GWF. And if you could touch on, hi, good afternoon, Ravi. If you could touch on how sensors are improving water management, what are the critical contribution Global Water Futures is making, and what are challenges and gaps? So we will go first, Claude, you, then Ravi, and then Helen. And then we can see if there are questions.
Yeah, so I'm a specialist in remote sensing. So I think for the questions, I will provide my perspective from remote sensing, using sensors to look at water quality and quantity parameters without being in touch, in contact with the objects. So from a distance. So that's the remote sensing, and that's because it's my specialty. So our research and that of others and different projects involved in the Water Futures are either developing new sensors, some of them which are remote type of sensors, and as well as algorithms that to process the data that we're acquiring from these different devices. So just to talk about I guess the first question, which is how are sensors improving water management? For me, basically, the technology we're working on and the algorithms, it's to improve the monitoring of water resources, the quantity and the quality, which of course can help for water management. So it's always been the case from remote sensing that it's been providing very broad spatial coverage. So that's a big advantage of, especially if we look at satellite technology. But at the same time, we've also been increasing in the recent years the temporal resolution. So that means we get a greater frequency of acquisitions from these satellite platforms. It's by no means right now replacing in situ ground-based measurements, but it's definitely improving in that direction. And what's been pushing this evolution is the private sector has been doing an amazing job the last 3 or 5 years by developing and launching constellation of satellites, these CubeSats, which are 10 centimeters by 10 centimeters by maybe 30 centimeters. It's called the 3U satellites. They're not heavy, but they can carry the sensors that are been miniaturized over the years. So that's really, there's a lot of work being done in that aspect of developing the technology. The other aspect also from improving water management has been from some satellite sensors. Some satellites have been in orbit for series over 20, 30-year periods. And now we've got some very good long time series that we can use to look at changes in water-related parameters. I can think of changes in the extent of water bodies, water levels of large lakes, surface water temperature, ice cover, water quality parameters such as chlorophyll A and turbidity. And so now, there's some. Of course, we always need to make some improvements on the sensors and the algorithms that we're working on. But there's long time series now that are available that can provide us with some pretty good ideas of the changes, the trajectory of and patterns across lakes and between lakes and regions over relatively long time periods from a remote sensing standpoint. Now, the next thing, of course, in terms of improving the management or the monitoring of these resources is that we're also looking at constellations of satellites from not only from these companies with small sats, which have hundreds, they deploy hundreds of small satellites, but there's also the space agency, Southern Kane Space Agency, which is not too long ago, they launched a constellation of 3 satellites where they can actually monitor changes, the monitoring of flooded areas, and that can be done on a daily time scale. So remote sensing and that aspect is really contributing to more and more providing better data for water resource management. Now, in terms of global water future and what it's been making in terms of contributions, there's several projects, or within even some projects, there's been different objectives. We're looking at either developing sensors or using existing sensors in collaboration with companies that are deployed either on towers. So we do some deployments on towers, field-based measurements to test the technology. Then some of those actually are used afterwards on what we call suborbital platforms, such as drones and airplanes. And of course, we're collaborating as well with the private sector with new CubeSats. Small satellites are being launched. And there's been a tremendous advancement been made by these companies the last 3 or 5 years. So I just wanted to provide you with a few examples of what, for example, the project I'm leading, which is TTSW, Transformative Sensor Networks. There's work being done by the group of John Pomeroy at Saskatchewan that are been developing and testing an acoustic system for snow. It's called Keone. And there have also been discussion as well about commercializing this sensor. They're also testing ultrasonic sensors, and these are tower-based, but there were also some plans on deploying some of those on drones. There is work of Richard Kelly at the University of Waterloo where he's finally going to be able to fly radar sensors on board of aircrafts to estimate snow, work on some algorithms to estimate snow water equivalent, freeze-thaw cycles of the ground, soil moisture. There's the work of Aaron Berg of University of Guelph, who's also working with private sector, where for the first time they'll be deploying a radiometer, which is this passive microwave instrument, to measure soil moisture on board of a UAV. There's also been some work on GNSS. So basically the GPS signals that you know about are being reflected by the Earth's surface. And some of that is measured by other satellites in orbit. And using that technology, we are working with companies such as Spire, which has a constellation of over 100 satellites in orbit right now, where they carry GNSS technology, and we can work with them to develop algorithms to, determine, to actually monitor freeze-thaw cycles of lakes, soil moisture, freeze-thaw cycle of land as well from this type of technology. And finally, we've been also working with NRC, National Research Council in Canada, where there's been hyperspectral systems, which is optical with many bands that are very useful for determining water quality parameters. And so we had the big field campaigns and airborne deployments, this type of new system developed in Canada called WISE to map chlorophyll A, phycocyanin, which are indicators of algal blooms. So there's a lot of work has been done in the sensors development. A lot of work has also been done on, we've been talking about, nowadays we talk more and more about AI, artificial intelligence, but really the algorithms behind them, there's machine learning, deep learning algorithm, neural networks. And so several members of these, of our project and other projects have been working on developing algorithms, machine learning, deep learning algorithms to improve our determination and monitoring of water quality parameters. And also, of course, ice cover. And finally, GWF has been contributing to the design of satellite mission concepts. So where, from an hydrology perspective, we know what the type of we had surveys where we determine which would be the best type of systems to put on board of satellite mission to monitor different water quality and water quantity parameters. But that's also informing both industry and space agencies for future satellite missions these are the types of wavelengths, frequencies you would need to monitor different parameters. And so we're providing that information to these agencies. What are the remaining gaps? That was the last question. Which one of them is definitely dedicated satellite missions. We've been talking a lot about the need to monitor map snow water equivalent at high spatial resolutions, in the order of 100 meter spatial resolutions, or 200 meters, or so on. There's some work being done in that respect. It's being considered by Canadian Space Agency. And some of the work we're doing through, for example, Richard Kelly with deployment of radar sensors on board of aircrafts. That's informing some of these future satellite missions, at least for consideration at this point in time, as well as the work we've been doing on hyperspectral and machine learning is also contributing to development of the WaterSat mission, which is another sat mission being considered by the Canadian Space Agency. And finally, I would say another gap is, of course, we'd like to have a dedicated hydrology satellite mission. There is one which is coming soon, which is SWOT, Surface Water Ocean Topography, which is a joint French Space Agency and NASA mission, but Canada is contributing to this as well. And it's for measuring especially changes in water levels, but of much smaller water bodies than what we've been able to do till now. But there's a need to take advantage of these constellation of small satellites where you can actually put 2 or 3 sensors on board that can cover, hyperspectral with miniaturization of these sensors. And we're starting to look into this in collaboration with King Abdul University of Science and Technology that are developing a micro hyperspectral sensor to put on board of one of the Spire satellites together with GNSS. And finally, there is still some need to advance the retrieval algorithms for all these parameters I've been talking about, related to water quality and quantity. But that requires a lot of training data, so there's definitely a need for more field measurements of some of these, for example, water quality or quantity parameters, and to train these deep learning algorithms, because they need a lot of data to be able to train and to provide better predictions of these parameters.
Thank you so much, Professor Duguay. So that is a good segue to Dr. Ravi Selvaganapathy from McMaster University. If you could tell us a little bit again, the 3 questions that we're talking about is broadly how are sensors improving water management? What are the critical contributions Global Water Futures is making? And what are the remaining gaps and challenges?
Thanks for invitation to this panel. So I think Helen would be the best person to describe how sensors are changing. So I'm also a sensor person, much like Claude is. And from my perspective, what I see is that what sensors do is to bring information at a local level in a continuous real-time basis, and then with that information, there's a lot of things that can be done at a decision-making level on managing water, whether it is surface water, groundwater, or other sources of water. So that definitely more information is always useful. Real-time information is useful. And so part of what we are doing within GWF is complementary to what Claude has been doing. Claude, if I take the analogy, is looking at the bird's eye view of things. What we are doing is looking at sensors in the field, doing the ground truthing that can sort of correlate the data that Claude is collecting, but also collecting data in places where it is hard to reach from the top, for instance, or providing information such as water quality information, chemical species information that may be difficult to obtain in other ways. So these two would be complementary approaches to collect as much information as possible. So GWF is contributing in terms of making investment where there's an integrated approach to doing things. So we, in the project that I led, we had one where we took existing water quality sensors and combined it with low power, long duration sensing systems that function almost like a network for cell phones, for instance, right? So basically you can deploy them in the environment and then collect information over a long term without expending too much power, running on batteries so that information can be continuously collected. So that was considered as sort of a preliminary stage where existing sensors were available, but these sensing systems were still high cost. And as we reduce the cost of these systems, what you would find is that it becomes much more easy to deploy these systems on a more widespread basis. And then researchers such as Helen, as well as other people, would find interesting and novel uses on how to use that information for practical purposes, right? So an example that I can provide is all of our smartphones have this accelerometers or gyroscopes, and originally they were developed actually for deploying airbags in automobiles, right? And then they became so cheap that they were under $1 a piece that Nintendo decided to put it into their gaming controller, and then that exploded the market, and Apple followed, and then now you see that every phone is now smart because of its ability to sense. And so one could not have predicted how that particular piece of technology would impact, say, for example, consumer electronics or other areas. And that is what we hope to do by developing new sensor technologies which are low cost, so that it becomes easy to deploy, and then you can deploy it over a large area, collect much more real-time information, and then provide it to water quality researchers in terms of water management. In terms of gaps, where I see gaps is that we have looked at certain parameters that were of importance for us in GWF, but there's many more parameters that are available. What I also see is in the future, this kind of distributed sensing, as we talk about in the sensing area, is going to become more and more prevalent in all aspects of our life. It's already entered in the consumer electronic area, at our homes, and so on. It is going to become much more important in environmental sensing. And lately, with the COVID epidemic, we've seen that it has become important for public health as well. So sewage monitoring, Mark Servos, one of our members, he's been doing that quite a bit, and so that has become now a go-to tool for public health to understand what is happening in the community at a community level. So I see similar kind of things happening for environmental monitoring as well, but that requires a lot of resources and continued investment in developing, again, reducing the cost of these sensors and sensing systems, making them in a way robust enough that they can be deployed over long term. So biofouling, for example, is an important issue that has not been tackled in a significant way. So as we do more and more in that area, we would see that sensors can be deployed, say, 6 months to a year without necessarily somebody having to go and maintain them. And it is at that point you have a tipping point where it becomes much more easy to deploy these sensors, and widespread use occurs, and that data can be used in a wide range of ways.
Thank you so much, Ravi. And on to you, Helen.
Great. Well, I think I'll take us in a bit of a different direction. Claude and Ravi have really filled us in on, I think, some of the really exciting developments in GWF and beyond, and in particular, the technology. And I think, you know, as Ravi points out, we don't always know how we're going to use technology. So I think that makes it really exciting. But I'm going to focus on the part about sensors to management. And I was thinking about this as I walked to a piano lesson yesterday, but To me, water sensors and some of the new models being developed are really as exciting as something like the Human Genome Project for the aquatic sciences. There's just massive, massive potential for leaps in our insights, and also in, changing how we handle things like aquatic ecosystem health. I personally see sensors impact so many areas of my work, understanding ecology, metabolism, early warning, and across GWF, we see it in flood predictions, things like boundary objects for capacity building and community engaged research, and so on. So I think the challenge becomes, partly on the development side, because there's so much work on new sensor development, but it's really achieving that potential of sensors and the potential of integrated data management. And Claude also touched on that, the different scales and histories of data that we need in decision making. So how do we move from these big models and big data to those insights? And then how do we use those insights in water management? So I think, it's a huge question we're sort of grappling with, of how do we use sensors in water management, and, that breadth of sensors from that we can use in flood prediction, the turtle sensors, drones, remote sensing, and so on. And certainly some real potential of sensors and apps in informing engagement decision-making as well. But I think my role is really to talk about a case study of how I've used sensors and the idea of partner-driven work or even transdisciplinary work to help inform water management. So the short version of the story is about 10 years ago, I wrote a grant to buy a new sensor system. And just before I did, I met with a water treatment plant to say, hey, this might be useful to you. And they agreed and thought it might be. So I gave them access to our streamed data. And through, the 10 years or so that have passed, we found it sure was useful. And indeed, arguably critical. They've just invested in the replacement equipment. The sensors that we've deployed in Lake are used day-to-day by operators. They're used to troubleshoot issues and have helped mitigate critical events that led to major water shortages. So they've really helped us understand the ecosystem, as well as how that ecosystem interacts with the engineered system for better management. So those sensors are a really important data stream, but I'd also argue they're an important boundary object for a strong partnership. So they allowed us to build that initial connection. And then from that connection and the conversations we have with operators and so on, we really have started to understand and manage the system better. So, some of the really interesting pieces of those conversations have been things like knowing when they're having process-related issues, and then talking about the fact that that actually overlaps with key periods of ecological change, and discovering, partly through luck and partly through listening, that indeed, these seasonal changes in ecology are leading to seasonal changes in engineering challenges, and we can use sensors to help, develop decision trees and adapt from there. So I think, the challenge is, it's a plant that I work with that's really benefited from these new sensors. It's also a plant with a lot of capacity and connections to universities. So as we think about more sensors and more data, I think the question becomes, how do we get the maximum benefit? How do we scale the successes? And how do we do that, particularly in often small, rural, and remote communities? So this question of capacity for improved decision-making based on the science and data we can now get. So those are pretty huge questions, and they're not so different from ones we heard in the previous panel. And so on. But I think certainly, huge progress on the technical side, and we need to really catalyze similar progress in engaging sensors in water management.
Thank you so much, Helen. That was really a wide overview of from remote sensing to ground-based sensors to use of sensors in data management. Since we have only about 20 more minutes, I'm going to kind of try to wrap what I had to say related to one of the questions that came out through the panel, because I think what I want to say is related to that. Would it be possible for all these sensors to provide too much data? How do we sort through all this data to find what is relevant for decision making? How do we prevent decision paralysis? And I think this is where Global Water Futures is also making a lot of headway. And that is a lot of our work in Lake Futures focuses on that, and as well as some work we've been doing in collaboration with Helen in Prairie Water, right? How do we get these different data streams at different resolutions? Sometimes you get daily data, sometimes you get every 2 weeks data. And how do we use various modeling platforms, from process models to machine learning models to exploring the data to gain insight about these systems? So that's one of the kind of big pushes, is data to model to decision to insight, and how that helps in our decision making. So as an example, in our particular system, we've developed machine learning models that can predict stream phosphorus concentrations across the Great Lakes Basin. And those kinds of models help us get insight into what are the drivers of higher soluble phosphorus. As an example, when you have reservoirs in the system, do you get more soluble phosphorus? So we're trying to tease out these insights based on the data that has been collected. And as more and more data is being made available through various sensors, both remote sensing as well as ground-based, kind of figuring out ways to integrate these information to provide insight that will be usable for decision making, right? So for example, just as an example, one of our results in the Great Lakes Basin shows that you get more bioavailable phosphorus if there is more livestock in the landscape. And bioavailable phosphorus is relevant for algal bloom. So these kinds of things allow us to get a little bit better at management decisions about how we can address some of these questions. And the funding and the support provided by Global Water Futures has made a tremendous contribution in getting us there. In terms of challenges, I think one of the biggest challenges that I personally, with our work, see with data is the different spatial and temporal scales at which these data sets are available, and to be able to use them together as opposed to each one in themselves. So harmonizing the scales of data availability. And of course, I would also say, in spite of the fact that it looks like we have too much data, we never have enough data. The heterogeneity of our landscapes are so huge that we are always lacking in data. So techniques like what Claude was talking about are really valuable to upscale remote sensing and the techniques to be able to look at some of these questions at larger scales, at which a lot of the larger scale management decisions might be relevant. So with that, there's another question, and this is a question I think for Claude. As Claude mentioned, training data would be important to improve retrieval algorithms. How do you think we can overcome the barrier of upscaling field data to medium resolution remote sensing? Are you muted, Claude? You're still muted.
Yeah, I know. Yes.
Okay.
I'm only using a laptop right now. It's usually I have the big screen, so I lost it at the bottom. Yeah, it is an issue that we have been dealing with, and actually working with Helen. It was not only a question of scale, but it's also reconciliation of data sets. So let's imagine you're working for remote sensing. You're trying to work on some algorithms to retrieve, let's say, just chlorophyll A. Then we talk to Helen and they say, well, in the field, there's maybe 4 different ways that we can determine chlorophyll A. And each of these approaches are providing you with a range of chlorophyll concentrations. So from a remote sensing perspective, how do you deal with that? What I can say from the remote sensing standpoint is, even if we can be off, at times in terms of the accuracies, I think to start with, can provide you with the broad patterns of places where things are changing, where concentrations may be higher, but then it's the field data, like I said, and how you reconcile the two. But for the training data, yeah, we always need more training data. We work with Helen, and she has our buoy at a certain location, the Buffalo Pound Lake, and there's Peter Levitt at University of Regina who's measuring with another method somewhere else on the lake, and then we have these various sources data and trying to come up with the good retrieval algorithms to map flow field concentrations. So definitely there's one step there between the field measurement and the satellite. But then we're using higher and higher resolution satellite data. There's more available from these constellations of new satellites that they can provide you with, sub-meter spatial resolutions. And then we have the Landsat type with maybe 20, 30 meters, or Sentinel-2. And then we have the Sentinel-3 with another 300-meter resolution. So there's some data that from satellite perspective exists to do this upscaling, but another challenge then becomes they don't have all the same spectral bands. Some of them, which may have very coarse resolution, have the ideal spatial wavelengths that you need for the water quality parameters. They were developed originally for ocean applications, but they're very useful for lake applications, but they work well on big lakes. If I take Buffalo Pound Lake again, you may only have 1 or 2 pixels of that satellite over Buffalo Pound Lake. It provides you probably with the best, I would say it should provide you with the best results given the spectral bands it uses. But then once we move down to the 20 or 1 meter spatial resolutions, the bands that were selected were not originally selected for water quality remote sensing, or water color remote sensing. So then we were dealing with, we have better spatial resolution, but we don't have the ideal spectral resolution. So the results will not be as good as the other sensor, which has much coarser spatial resolution. So it is a challenge. It's the scaling. It's only the pixel size. It's also the instruments you have on board of these either drones or satellites that have different spectral bands, and the measurements in the field that you use for training these algorithms, which each have their source of error. So there's a lot of uncertainty in these estimates.
Thank you so much, Claude. Others? Either this or the other questions about how do we have when we are swimming in data, not go with decision paralysis.
I think that's a really interesting and important point of, on a lot of water management, we actually don't need more data. More data can help us with adaptive management, but some of the decisions we should be making, we actually have a lot of data on already. So I think I liked that question a lot in terms of, bringing us back home on you can drown in data, but sometimes you actually have the insights you need already. And it's that next step of action that's needed.
Maybe it's also in our strategy to, I think we have to become more intelligent in how we process. Big data now is not an issue. We've processed a data set of 1.2 petabyte of data recently, global, and you have supercomputing infrastructure. It is possible. I think it's going back to the board, experimental design and so on. It's how do you deal with, how do you approach it, and how do you sift through, and how do you filter and so on. So I think there's strategies that exist for not becoming overwhelmed with the amount of data that streaming. Even from a satellite perspective, there's now algorithms that you run on board of satellites that will, for example, detect clouds. So they say there are clouds, it's not useful data, so we'll just download the useful data. So it's all being processed on board of satellites. You don't need to downlink to a satellite and then run your algorithms on your computer or supercomputer to derive this. There are ways, there's some very smart young people out there that are working on this type of work, this type of approaches. And to me, it's not a huge, well, from what I do anyways, it's my perspective. It's not too much of a big challenge nowadays. But
thank you. Others? Ravi?
Yeah, I think, I share the perspective in the sense that, if there is that there is enough data, or there is lots of data, one can pick and choose what we want to use, right? So and that is where the judgment comes in of the user, and the availability of rich sets of data allows different people to ask different kinds of questions, right? And historically, what we have had was problem of lack of data. So the analogy that I'll take again is when I was a student, you have to go to the library and photocopy a journal in order to get information, and that is how information collection happened. Now with Google and all of these things, it is at the fingertips or your computer screens, and very often, if you have a hypothesis, you could basically do thought experiments on different aspects of it and search for appropriate papers in different areas, and get good reliability of that, right? And that is what a lot of data at your fingertips allows you to do, is to ask these questions, which in the past we would have given up because of the amount of effort it would take for us to set up that infrastructure and collect and all of these things, right? And now when the data exists already, then it is much more easier to do this. So what it does is it removes some of the impediments that people may have in asking questions which may not necessarily be highly significant at the start, but which may end up becoming much more significant later on, right? And so it's a good place to be. Data curation, of course, is an important problem, right? So tagging the data and so on, and this is something that we've discussed in GWF as well, is that data by itself is not very useful if you don't have the relevant tags and signifiers associated with it. And so curation of the data, preservation of the data becomes much more important for all of these purposes. And so that's where, again, a gap exists and should be thought about.
Thank you. So I don't see any more questions in the chat. I'll ask another question to the team to see what people. So I'm at a meeting this week, and there's a lot of conversation about open data and open science. So I wanted to kind of throw it back to you guys to see what you thought about, like, as more and more data becomes available, the value and challenges with open data.
The challenge to me is to convince researchers to share their data. That's the biggest challenge. Open data, it should be open data. There's no doubt about it. You know, when we retire, for me, maybe 4 or 5 years from now, I want the next generation to use that data, not to, you know, keep them in a folder on a disk drive in my basement somewhere. You know, so open it, and that's the way that, you know, science can progress much faster. Is that there's some good data for environmental changes. You know, again, using the satellite aspect to this is, if you want to look at changes in some water quality parameters over a 20-year time period, and oh, geez, there was some data, some field data acquired, you know, collection made 12 years, 15 years ago that you're not aware of, you know. And knowing that this data does exist, at least if researchers don't want to share the data directly, at least to, as Ravi was mentioning, you know, metadata, you know, documenting the data is available. And of course, GWF has a policy for this as well, that we should be sharing our data. At least have the metadata and the contact of the researchers that owns the data to make it available. And I think at the insert level as well, it's strongly encouraged not only our publications anymore, but as well our data to be open access. So it's a must.
Thanks so much, Claude.
I agree. It's a key area, and I think the area of data rescue is really important when we think about people close to retirement and some of the data that is not published. But I think another challenge is data curation, right? So by engaging in sensor-based measurements and all of the QA/QC involved and so on, you're also signing into data curation. And how do you get the time and money to do it all is a real challenge under existing funding models. But I think, the flip side of that is if we have an economist in the audience who wants to estimate the amount of money invested in stranded data, it would be utterly massive. And it's a real impediment because we can't go backwards and fill data gaps that we wish we had numbers for. So it's a key priority. I did read something, and I wish I remember where, that may be a good opportunity to remove people's reticency here. Like, I think field-based researchers like me remain reticent because we invest so much in these data, and some of the data are nuanced and need translation. And it is basically that, you publish your data, but then henceforth, the people on that data publication are co-authors when it's used. And I thought that was an interesting and I'm sure controversial idea, but it might change that landscape of the people who are resistant still to publishing their data.
Thank you so much, Helen.
And I think, open data is always good. There's lots of benefits to it. One sort of limitation or things that need to be thought about is privacy, right? So it is location-based data on information that the society has not normally dealt with previously, and therefore that can cause changes in all kinds of things. So, for example, property values may go different if you analyze the water quality and release that information on a periodic basis, right? So those are all things that at a societal level can potentially affect when data is released. Another is indigenous communities, so they want ownership of the data, and therefore that is also something to be cognizant of. And again, as this becomes more prevalent, different communities may want to not release the data or release the data. So the data ownership is an evolving issue in the case where, environment is a common good, but then if a stream goes through somebody's property, is that private data or public data? That's something to be worked out as well.
That is really true. There is a ton of data out there. That is, the privacy issues of the data is another really big and contentious issue, specifically when we work, with a lot of data that kind of falls within those bounds. Okay, so we have 2 more minutes left. I do not see any other questions. Any last thoughts? Okay, thank you all so much for your time. This was really, really interesting, looking at kind of the landscape of sensor data in GWF, both in the space of what it's used for, as well as what it takes to some of these data and the advances made. Thank you so much for all your time. Have a great rest of the day. Take care.
Thank you. See you then. Bye.
Have a good night. Bye.
Bye.
Bye, everyone.
Hi, everyone. Thanks for sticking around and welcome. We're just at the end of the last session, and it's been a great meeting so far. I'm Science Manager for Global Water Futures, Chris DeBeer, and I've been participating in this meeting from Saskatoon, which is Phase 6 territory and homeland of the Métis, and I wanted to acknowledge that. And now we'll bring on the Associate Director of Global Water Futures, Corinne Schuster-Wallace, to say a few closing remarks.
Thanks, Chris. I really appreciate all of the work that you've done to make this meeting a success. I'd like to share, as with previous INL Open Science meetings, a formal statement of what we've heard and what we've learned. And it's been a lot this year for sure. As we're aware, Global Water Futures has amassed a large amount of knowledge through through research and is working with many partners and collaborators, including Indigenous partners, to better work across knowledge systems and within the uncertainty of our water futures in Canada. Over the past 5 years of the program, we've completed laboratory, theoretical, fieldwork, and community research activities, as well as modeling, visualization, sensor, and tool development. And we've helped develop the first national water prediction models for Canada. We continue to synthesize research findings through workshops, sectoral meetings, model applications, and publications, of course. And we need to continue these synthesis activities in collaboration with our research partners while continuing our communication and outreach through regional and sectoral science discussions and custom knowledge translation applications. And as we've heard so many times in the past few days, this is really timely given the extreme water energy events experienced across Canada in 2021. The record-breaking heat, drought, rainfall, melt, and wildfires that were experienced from coast to coast to coast, they weren't only of immense magnitude, but also remarkable persistence and national impact. And so several key messages have emerged over the past few days, and I'd like to share those if I can share my screen, please. Thank you. And so we've heard the importance of, and it's been re-emphasized, the importance of collaborative and reciprocal partnerships, partnerships between disciplinary experts, partnerships with Indigenous and other communities, governments, organizations, and businesses to reduce the disconnects between discipline sectors, urban versus rural, upstream, downstream contexts, knowledge systems, languages, and scientific information versus public information needs, which again was highlighted in the last panel. The importance of open minds and active listening as part of knowledge mobilization. Engagement starts at the conceptualization of research and needs to be continued throughout, listening to concerns and ideas, working collaboratively to generate solutions. The importance of working across knowledge systems, harnessing process knowledge and quantitative and qualitative data, developing holistic and community-informed models, and reconnecting and reconciling not only with each other, but also with the environment. The importance of co-developing water governance systems in Canada using multiple knowledge systems and braiding Indigenous and current colonial mechanisms. The importance of better and more extensive measurement and prediction systems. We've also recognized that we are not ready for water-related climate change impacts that we will continue to experience. And we've also recognized that we need a different way to proactively manage water-related disasters and reduce risk. The recognition that in mitigating water-related risks, we need solutions that account for biophysical, social, cultural, political, and economic contexts, while ensuring that risk is not displaced to other types, groups, places, ecosystems, or times. The recognition that vulnerability to water-related risks is interwoven with issues of social and environmental justice. The recognition that the Canada Water Agency can be a critical catalyst to achieving our sustainable and equitable water future, but this is only as long as it's given the requisite agency and mandate to act effectively, and that it does so within a collaborative governance structure. The recognition that there are many opportunities to learn from success stories, both within Canada, for example, Manitoba's Collaborative Leadership Initiative, but also internationally, Aotearoa's Water Future, for example. And finally, the recognition that tremendous knowledge, data, and tools developed in global water futures need to be preserved, but also made accessible for current and future generations as they seek solutions for a more sustainable and equitable water future for Canada. Ultimately, the climate crisis is the water crisis, as we're all aware, and we need partnerships to create innovative, equitable, and sustainable solutions. We need to ensure that all voices are at the table, and we need creativity, imagination, intentionality, and transformative thinking to lead us towards more sustainable water futures. So on behalf of John and myself, thank you for another great annual Open Science meeting. But before Elder Duquette formally closes the meeting, I need to recognize the many people who've made this meeting possible. First and foremost, the speakers, chairs, and you, the audience, for delivering on my opening hope that this meeting catalyzed conversations and forged new partnerships as we continue to generate knowledge to inform equitable and sustainable action. Specific thanks go to my co-chair, Chris DeBeer, as well as the rest of the GWF Secretariat, Andrea, Cal, Fred, Jesse, Mark, Michelle, Fanny, and Viviana, the Strategic Management Committee for Global Water Futures, the Global Water Futures Young Professionals, and Pearson Technologies. Thank you, everyone, for making this a success. Really appreciate it.
Thanks, Corinne. Yeah, that's. I'm glad that you said that. I was going to say that as well. So, thank you, and I repeat that. Can't express the gratitude enough to all the speakers and to everybody who contributed to making this a success. One thing I've learned is to clearly communicate time zone differences, as long as you don't want that to come back to haunt you, because it certainly did for me. So that's something I'll take going forward. As John mentioned at the beginning, we're looking to have our next meeting in person, so stay tuned for that. And just one point, that all the sessions and posters can be viewed on the website for the coming weeks. So now I would like to hand the floor over to Elder Roland Duquette to close us in a final blessing.
Roland, I'm sorry to interrupt you, but you're still muted.
There we go. Good. If some guy to analyze katam skat now, kakio, kapiatuski, kapiam scott amigo bonipi. The kitchen tago, my kitchen ads. Am I still muted? Hello? Can you hear me?
We can hear you fine now, Roland.
Oh, okay. Thank you. Yeah. Just in closing, I just want to commend everybody, acknowledge and recognize the speakers, the guests from wherever your bonfires are from, that you go back to them in a good way, in a healthy way, in a warm way, and also to know that we all have that same use of water for our livelihood, for us to know that we survive with it. Without it, we struggle. Same with life. If we don't have an inclusion of people, we struggle. But today, inclusion is so important, that we have an awareness of people that have one understanding, one thought of survival, and it's that water. And I think that if we start kind of dissecting, areas where the water flows, then people will struggle. So inclusion is so important. And I think that's my message today, is to have that awareness that water is vital to our neighbor, vital to our communities, vital to our land, vital to our world. So it's a worldview as well. So we cannot lose that sight. We have to be aware. So that's how I pray and ask Creator to give you that full understanding of yourselves, first of all, that you control that. You have that awareness within yourself, with your spirit, your soul, however you believe. And it sends a message to your mind, to your thought, to what you can see, that reveals to you in a way where it flows like the mind. It flows wherever it's needed, it flows wherever it's wanted, So that's how we try to maintain our creation story, So that's my message to everyone that's listening today. And I thank you all for being there. I'll never say it's it's done, no, but later, Moistas, that's what it means. Moistas, it's a carrying on, We cannot end it here. There's no ending to that. Same with life, It's continuous. It's it evolves into that connection. One goes, another one sets in there. It's just a follow-up, a rotation. Same with crops, That's the way they should be treated, Land should be treated like that. Give it a rest, So that's one of the key areas where I'm very concerned how we're going to survive our land and our water. So ksara tutam skat na kakyo kamyuki ono kamyuki second snow mina motio chinya kutas tapamas kia kauchianya yagame mita ko kakyo can stolta make yagama matsun. I thank you all again later.
Thank you so much, Roland. Goodbye, everyone.